Okay, so on the last slide, we just quickly took a look at what work you'll need to show for the AP exam. So this you can obviously plug directly into your calculator. You have two choices for the AP exam. You can either show the numbers plugged into this formula, then do the work on your calculator, or if you want to show the addition formula of adding everything up, you'll just have to show the first few numbers plugged into the formula, such as maybe like the first and the last one. Actually, I would use your calculator to get the actual results and the actual answers, but just make sure that you show the plug-in into that formula and you'll be good to go. All right, so how exactly do we find binomial probabilities? What work are you going to need to show whenever you're doing these types of questions? All right, number one, you're going to have to state the distribution and the values of interest. So this is very similar to what we talked about in our previous units with the normal distribution. You have to state approximately normally distributed, mean, standard deviation. In this case, you're going to say binomially distributed B with the number of trials N and the probability of success P. So you have to make sure that you clearly identify that you're using a binomial distribution. So you can just define X. X is the number of sixes that we get when we roll a dice 4 times. Make sure you're defining what that X value is, state what the distribution is, and then fill the values in for N and P. Make sure you do your calculation, show your work, so you can use that binomial probability formula. Just show the numbers plugged into that formula. That's all you need to do to show your work, and then always make sure that you answer the question in context of the problem. All right, so let's just go ahead and try a couple of questions, see what work we need to show, and what exactly that looks like. So each child on a particular pair of parents, this is going back to that type O blood probability question, has a probability of 0.25 of having type O blood. Suppose they have 5 children. Find the probability that exactly 3 of the children have type O blood. All right, so what does that probability statement look like? Number one, let X equal the number of children with type O blood. And then here's where we're defining it. X has a binomial distribution, N is 5 because there's 5 trials. The probability of type O blood is 0.25. Instead of writing out this second sentence, you could also just write B and then fill in N is 5 and P is 0.25. So B 5, 0.25. Okay, now notice how your probability statement isn't a greater than, it's probability that X is equal to 3 because we want exactly 3 to have type O blood. Now notice, okay, here's the numbers plugged into the formula. 5 choose 3, so I have 5. I want exactly 3 to have successes. Here's your probability of success. We want 3 successes. 0.75 is your probability of failures. We want 2 failures, and then 5 choose 3. There's 10 ways that can occur to get 0.08789. Now this is fine. You can just leave this the way it is. You don't have to write out that 10. Just show those numbers plugged into that formula. All right, now here's the next question. This is going to look a little bit different. Suppose should the parents be surprised if more than 3 of their children have type O blood? So to answer this, we're finding the probability that X is greater than 3. Now notice it says more than, so we're not you can say the probability that X is greater than 3, or the probability that X is greater than or equal to 4, okay, because more than 3. All right, so what does that mean? If we're finding the probability that more than 3 of their children have type O blood, that means 4 could have type O blood or 5 could have type O blood. So we have to add those two probabilities together because I have 2 possibilities. So here's your first one, the probability that exactly 4 have type O blood. 5 children, 4 of them have type O blood. Probability of success, 4 successes. Probability of failures, 1 failures, plus all 5 of them have type O blood. Probability of success, okay, 5 of them have successes. Probability of failures, 0 of them have failures. So then 5 choose 4, there's 5 ways for that to happen. 5 choose 5, only 1. Add up your 2 probabilities to get 0.01563. Okay, now since there's only a 1.5% chance that more than 3 out of the 5 children would have type O blood, the parents would actually be surprised if 4 or 5 of them had type O blood. Okay, now that could also get kind of cumbersome, making sure you're plugging everything into your graphing calculator. However, you can use Binomial PDF and Binomial CDF on your graphing calculator in order to come up with the probabilities. There is a step-by-step video tutorial in the folder in Blackboard. go to the calculator videos. It's under 10.3, Calculating Binomial Probabilities. So this is going to show you where you get the binomial PDF function on your calculator. Actually, it's going to say 5.3, not 10.3. Okay, so binomial PDF on your graphing calculator. What exactly does that mean? So binomial PDF is for your stands for your binomial distribution probability density function. So you'll use this when you want to find the exact number of successes in any given number of trials. All right, so on that previous slide it said, what is the probability that exactly 3 children have type O blood? So binomial PDF allows you to find the probability that exactly 3 or 4 or whatever, only one possibility have that probability. So on your graphing calculator, it's going to look like binomial PDF. You're going to type in N is the number of trials, so in that case 5 trials. P is the probability of success, 0.25. K is the fact that we want exactly 3 children to have type O blood. That computes the probability that X is equal to having 3 children, exactly 3 children with type O blood. All right, so we just went over that with the previous example, so if you want to go ahead and take a minute and read that, you can. Okay, so here's how you would actually do it on your graphing calculator. You're going to hit second, vars. Okay, so this is in the same place where you're getting like normal CDF from our previous units. You're going to scroll down until you see binomial PDF, 5.25, 3, and it's going to give you your answer. Okay, so just keep in mind, like I said, PDF is finding exactly 1, the probability that exactly, I'm not saying exactly 1, but 1 possibility. So exactly 3, that is 1 possibility, exactly 3 children have type O blood. Okay, if you notice right under binomial PDF, there's a binomial CDF. So same thing, for a step-by-step video tutorial, go to the videos and go to section 5.3, Calculating Binomial Probabilities. So what is the difference between binomial PDF and CDF? If you remember from our normal distribution, we only used normal CDF. Well, that's because remember with a normal curve, you have to have a range of values. So this is the same thing. Binomial CDF is a range of values. It stands for cumulative density function. You're going to want to use CDF, cumulative, so think like cumulative, you're adding stuff up, when you want to add the number of successes up to and including K. Okay, so binomial CDF, so same thing with the normal distribution. Whenever you compute a probability, it's always the probability less than or equal to that number, unless you type it in differently. Binomial CDF is the same thing. It's always computing the probabilities less than or equal to that number. So when I type in binomial CDF, N, let's say we did 5, P, and then K, so let's say N is 5, probability of success is 0.25, and I say K is 3 in this case, that's going to compute the probability that X is less than or equal to K. So that's going to compute the probability that X is 0, X is 1, X is 2, and X is 3 if we were taking a look at having 3 or less children with the probability of type O blood. So just remember that CDF adds everything up to and including the K value. And then students often forget here that there's always a chance that it doesn't happen. So don't forget, if it says to please write out the probability that X is equal to 0, because I could have 0 children with type O blood, 1, 2, or 3. So just be careful with that. Okay, so let's just take a look at what that would look like with our previous example. So let's say find the probability that less than 3 children have type O blood. So just be careful when you type this in. Okay, since this is less than, the probability statement is the probability that X is less than 3. Well, what exactly does less than 3 means? That means that 0 children can have type O blood, 1 children can have type O blood, or 2, but not 3, because I want the probability that X is less than 3. So then be careful when you're typing that into your graphing calculator with your CDF. You're going to type in 5.5, 2, 5 trials, 25% of probability of success, only 2. Why only 2? Because I want less than 3. If I put 3 here, that would calculate the probability of that third of 3 children having type O blood, but I want less than 3, so I want up to 2, which is 0, 1, and 2. Okay? All right, now it could get a little bit tricky when our questions are greater than. So we're sticking with our type O blood example question. We know that we have 5 children, the probability of success is 0.25. Now look at what the question says. Should the parents be surprised if more than 3 have type O blood? Well, our binomial CDF doesn't do more than 3, it only does less than 3. But we know that more than 3 means the probability of 4 and the probability of 5, okay? Because 4 children can have type O blood or 5, which would be greater than 3. Now, binomial CDF is only below the K value. So the possible number of children with type O blood from our example, we can have 0 children with it, 1, 2, 3, 4, or 5 children can have type O blood. But what do we want? We want the probability that X is greater than 3, so we want 4 or 5. Now keep in mind that this is 100% of the possibilities. 0 through 5 is 100% of the possibilities. We want to get rid of 0, 1, 2, or 3. We want to keep 4 and 5. So let's think about it this way. Let's think about using the complement. The probability that X is greater than 3 is the same as 100%, which is all of them, minus less than or equal to 3, because that's what we've X'd out, less than or equal to 3. So on the calculator, if we take 1 minus binomial CDF of 5.25 comma 3, that's going to give us what's left of the 4 and which is the 4 and the 5, because I've taken the 1 is all of them, subtracted out what I don't want, the 0, 1, 2, and 3, to get my final answer. Okay, so that's the trickiest part. All right, so go ahead and try these on your graphing calculator just to see, make sure you got everything good with your binomial CDF, PDF, all that good stuff on your graphing calculator. So in roulette, 18 of the 38 spaces on the wheel are black. Suppose you observe the next 10 spins of the roulette roll. What's the probability that exactly half of the spins land on black? Make sure we're defining X as the number of times the spins land on black, okay? And we know that we have 10 spins on the roulette wheel. So what does that look like? Notice I have stated that's binomially distributed. You must state that, 10, and then the probability of success is 18 out of 38. On the calculator, that's binomial PDF, 10, 18 out of 38 is the probability of success, and I want exactly 5. It's PDF because I want exactly 5. Okay, so what work would you need to show for your AP exam? So probability of X is equal to 5, 10. I have 10 trials, 5 successes. Here's the probability of success. I want 5 successes. Probability of failure, I want 5 failures to get my final answer. But you can do everything on your graphing calculator. Okay? All right, so go ahead and try this one. In a roulette, 18 of the 38 spaces on the wheel are black. Suppose you observe the next 10 spins of the roulette wheel. We want the probability that X is greater than 8. So what's the probability that more than 8 spins land on black? Okay, now think about this. X is greater than 8, so that means I want 9 or 10. So if I'm thinking about 100% of the possibilities, I want to take away 0 through 8. So I want 1 minus the probability that X is less than or equal to 8, because I want to get rid of 8, 7, 6, 5, 4, 3, 2, 1. I just want 9 and 10. So 1 minus the probability of binomial CDF, okay, because I'm taking 100% minus CDF is up to and including that number up to 8, okay, because I'm getting rid of that, which is 0.00688. What's the probability that at least 8 of the spins land on black? How is that different? That's X is greater than or equal to 8. So I'm going to take away less than or equal to 7, okay, because I want to include 8, so just be careful with that. I'm only subtracting 7 in this case, okay, because I want 8 or 9 or 10. Okay, so go ahead and take a minute and try this one on your own. Okay, let's just go over the answers. All right, so number 1, just make sure you that you state what we're looking at. We're looking at define what X is, the number of participants who prefer the last kiss they taste. What is it distributed? Binomially 22 with a probability of success of 0.2, and the probability that X is equal to 5. So that means I want exactly 5 of the participants to prefer the last kiss that they tried. Here's your calculations using technology, PDF because I want exactly 5, trials 22, probability of success is 0.2, and X value is 5 because I want exactly 5 successes, and then answer the question. There's an 18.98% chance that exactly 5 participants would choose the last kiss, assuming that there's no special preference.